Elias, for your talk and answers. And the last speaker of today is Reidmen AROSTICA from University of Groningen. So please, you can share your slides. Hello, Reidmen.
Hello, Christian. Just let me check.
The topic, in the meantime, I could say that the topic of the talk of Reidmen is a physiological benchmark for cardiac mechanics.
Yes. Could you please let me know if you can see
yes,
a presentation?
Very good.
Okay.
Very good. You can start, please.
Okay, just let me check if I can. Okay, perfect. Nice. So thank you all for coming to this last presentation, if I'm not wrong. So this is kind of atypical, but it's a title, A Physiological Benchmark for Cardiac Mechanics. As Christian said, my name is Reidmen AROSTICA, and I'm part of the Bernoulli Institute in the Netherlands, with the main leader being Cristóbal Bertoglio. Also, it's important to say this is a joint work, it's a joint contribution, also with TUM in Germany, and we have the strong support of Martin Faller at Stanford. So this presentation is divided in 3 sections. Briefly, we're going to give you a motivation of why we're interested in such a benchmark, then propose the problem formulation we currently have that of course can be modified, and finally, a brief summary. So, motivation. Why we want to define and propose such a benchmark? Is there a reason for it? First of all, we want to tackle the problem about reproducibility of all these results. Namely, if you have, for example, an estimated parameter, you would like to use it in a specific physiological model. Moreover, we want to have support collaboration with clinicians. Usually what happens is when you talk with them, a common question arises, being, have you validated your model? Is your model validated in some sense against real data? And there's still not many answers to that question. And lastly, but not less important, is the fact about that we want, if possible, to propose modeling strategies. In this case, could be which choice of considered models are physiologically meaningful, which boundary conditions should be taken into account whenever we want to talk about a benchmark, and also parameter value ranges. Now, what about the literature? Having done a review about what exists, we came up that the main work is done by Lance in his 2015 work. He proposed the first benchmark for cardiac mechanics software. Nevertheless, we noticed that it lacks several features that we think could be useful to be included. Things such as like geometry dimensions, real geometry dimensions, physiological, passive, active modeling, as well as boundary conditions should be included. And also, at the moment, there exists only software verification, but not validation. First, based on the previous points, what we aim here, and of course, we want to invite you and also encourage you to join us in our efforts to propose a new set of cardiac benchmark problems and solutions for assessing the passive and active material behavior of the heart. So now, what about the problem formulation? Of course, all of what I'm saying is just in the first stage. It can be modified based on any suggestions that you might have. So here we followed Lance's idea, in this case, modeling the geometry of the left ventricle, denoted here by omega. Such a domain is taken as a volume between 2 main surfaces, the endocardial and epicardial surfaces, parameterized using ellipsoid coordinate system. As you see there in red, those terms are highlighted only because we took them using static MRI images. And what about the fibers? So as in Lance's work, we take the fibers using the tangent basis from the ellipsoid parametrization of our domain omega. Fiber, normal, and tip directions are taken as explicitly given in the presentation, where I only want to emphasize this parameter alpha that is highlighted in green, that represents how the fibers move throughout the wall thickness from a specific angle at the endocardial surface to a specific angle at the epicardial surface. So this is a lot of words. So how does it look like? So briefly, in this small video, you see on the right side a mesh, an example mesh of the domain that we're proposing. On the right side, the analytical fiber description that I previously said. You see there in blue the epicardial surface, and in red the endocardial surface in a specific plus minus 60 degrees angle. So having defined the mesh that we're kind of interested in, what about the formulation? Here we want to, and we are proposing an elastodynamic formulation of the problem. Why highlight the first equation, in particular determined with 2 times derivative, is the fact that in Land's work, there's still not included the effects of the inertia and viscosity. In our model, we want to include them, and we also want to impose specific boundary conditions. Naturally, we want to include a pressure on the endocardial surface, denoted here by gamma endo, and at the epicardial and top surfaces, that's as you saw in the video previously, we want to enforce the so-called Robin boundary conditions. What they represent essentially is the effect that has the pericardium within the whole cardiac contraction. And that work is profoundly done by Fallers in his 2019 article. So what about the constitutive model? Here we want to propose, of course, it's subject to discussions, second pillar Kirchhoff stress tensor, as is done in literature, with 3 components. First, we take the energy, so-called anisotropic energy, characterized using the Hostoffen and Ogden description, that arises from 3 main contributions: a full isotropic contribution with the invariant A1, 2 transverse isotropic contributions for the fiber and T directions, denoted by the second invariant I4S, and a fully anisotropic contribution I8FS, where this last term denotes the CMO and Miehe incompressibility penalty that we are proposing. We also want to include the viscosity. Here we use the standard fashion characterized with a parameter eta. And finally, we take a time-dependent active stress expression, where the stress function is described by Bestel and arises from biochemical assumptions and is given as a solution of a very specific ODE. All of the description is specifically done in the papers below. And thus, we have the model that we are proposing, and I want to show you just a very simple example of how does it look like. That's the reason why now I'm presenting you the parameters. We take density, viscosity, incompressibility penalty, activation stress function parameters, boundary conditions as taken by Faller's work. And I only want to give you a glimpse of the table, just that you know the ranges in which we're using the parameters. We also take the Hochschild and Ogden model, characterized as in this article, that describe and fit parameters using the values from experimental data. And thus, how does it look like, all of this? So using quadratic elements in the simulation, you see a contraction of the ventricle where the field here is a displacement field. On the right side, you have a top view, and let me just play the video again. You see how it contracts and how the wall thickness changes through time, where in this case, just a very simplistic case, we have a pressure 0 at the endocardium. Importantly here, our results, we have obtained closely matched results with the TUM group in Germany, and also extensions for a time-dependent pressure. So this is our proposal, and what's the summary? First, and most importantly, we want to propose a first idea for a physiological cardiac mechanics benchmark. We want to provide results for verification of new software and or model components. Namely, many research groups already have developed, they have mature software, mature code, and thus we want to be able to easily propose a model that is simplistic enough such that they are able to reuse their code and check if their results match against some verification case. We have already contacted different groups from different countries, more than 6, 7, if I remember correctly. Many more we will contact, so maybe you'll get an invitation. What do you might expect from this? We want to have at least a joint paper for the verification problem and further in the future for the validation. Those two questions are very, very important to be answered. And at the moment, we think we haven't found out articles in that regard. Things to be discussed. Why this is important? Still, this is just a proposal, meaning we're still in the early stages and many things need to be discussed as soon as many groups join. Things such as the inclusion of the endocardial pressure, long parametric models. We could also add irregular electrical activation, pre-stress, infarction effects, etc. Things also such as the output quantities. How can we compare our solutions from the solvers? We can use stress, strains, displacement fields as we compare against TUM. And moreover, things such as how anonymous we want the solutions to be. How are we going to define this benchmark in such a way that it's meaningful for everybody and we obtain a ground truth case. And this essentially corresponds to the presentation. If you have questions, if I did something wrong, if you have suggestions, please let me know. Feel free to ask and feel free to tell me whatever you think it's meaningful. A more detailed description of this benchmark and presentation can be given in this bit.ly link, or easily you can just QR scan this specific code. And also you can contact us, Cristobal Bertoglio and myself, for more information and if you want to join us. Thank you.
Thank you. Thank you very much for this interesting talk about benchmark, which is a topic which always of interest, of course, for the community. Are there any questions from the audience?
Okay,
okay, Alexei Liocchi has posted a question on the chat.
Yeah,
Alexei, you can switch on your camera, and if you want, you can ask directly.
Okay. Good morning. I have a question. What is initial value of activation variable tau from T?
Yeah. Yeah, tau in the presentation. Yeah, okay. It comes from a specific ODE, right? And it starts at 0 and then activates in a specific fashion. That rises naturally. Yeah, but it starts at
from 0. Thank you.
And then increases in a roughly exponential fashion and then decreases.
Okay, Axel Lowe, please.
Thank you for the nice presentation. Can you summarize briefly again what are the additional properties compared to the LAMP benchmark that you were looking at?
Yeah.
And then I would have a follow-up as well.
Yeah. Okay. So let me see. Let me move that thing. Yeah. So maybe I didn't say that thing with enough time. So one thing, and I highlighted this in red. So the currently LAMP's work doesn't include that dynamic effects, right? So first of all, we're including what we think is natural, right? We want to include the dynamics in time. And also boundary conditions that are physiological. In this case, we refer to Valère's work. Physiological in the sense that we want to include the effects of the pericardium. And it's not that hard to implement because they're just rubbing boundary conditions, right? And also, since we want this elastodynamic problem, we're including, first of all, a viscosity term that doesn't exist currently in Land's work, and also a time-dependent activation function.
And regarding the activation function, did you consider including a stretch dependence there, which is, I think, a quite important mechanism when looking at the physiologic behavior?
Okay, I haven't thought about that, but it's that. Thank you for that remark, because it's very important. Yeah, thank you for that.
Thanks.
Okay, thank you, Axel. Elias, please.
Thanks for the talk and for proposing this benchmark.
Yeah.
In your dynamics for the structure mechanics, do you think it would be also beneficial to add a damping term to the first equation?
You mean, yeah, no, it exists. It's described in the second planar Kirchhoff stress tensor. Yeah, there.
Okay, you damp by the viscoelastic.
Yeah,
but
so
okay.
it's damped. Yeah.
Okay, because if you just use this, use the second time derivative, it might, get unstable and harder to solve.
Yeah, of course. Yeah. Otherwise, we'll be like exploding in our solvers. Yeah, of course. Thank you.
Okay, thank you, Elias. Other comments or questions for Reidmen? Okay, if not, we can thank him and all the speakers of of today, of this afternoon, the two plenary speakers and the contributed speakers. And I would like to remember that tomorrow at 2 p.m. European Center time, there will be the third and last day of the conference. So we wait for tomorrow, and thank you again.
Thanks.
Good evening.
Have a good evening.